Hello everybody. One of the things I've been thinking about recently are the batteries I've been using to calculate their discharge curves using the circuit that I created with the Arduino, which I'll put a link to on the screen. And what I've been thinking about is not just the chemical characteristics of these batteries, but really what investigations can we carry out ourselves into the kind of the composition and the discharge. And is it possible for me to make a battery that actually performs as well or better than these commercial ones that I've tested so far? So I've been thinking about a Voltaic Pile, an old-fashioned the battery that was created in, I think it was 1799, 1800, which was alternating layers of, well, in this case copper, and I'm going to use a 2p coin, and aluminium, but any two dissimilar metals will work. The further apart they are in what's called the electronegativity series, the higher the voltage of the battery, but actually any two dissimilar metals to some degree will produce a voltage when you separate them with an electrolyte. So you make a sandwich. I'm going to show you now as a dry sandwich, and then we'll make one properly. We take an alternating layer of copper, and here we've got some lovely, nice clean copper coins, 2p coins that I've cleaned. And that's a whole source of another video and something interesting. But those coins that I've cleaned, just to get the copper oxide off the layer of the coins. And very often children like investigation into what cleans copper coins anyway. So copper coins, I'm going to start with the copper coin, and on top of the copper coin I'm going to put a layer of electrolyte. And what I'm going to do is I'm going to draw around the copper coin, and I'm going to make a series of cardboard discs. So if I cut around, draw around the copper coin, and I cut out some cardboard discs. And in this case, I'm going to make 4, cut them out, and then I'll edit the video, so you don't want to see me just doing this. But we're going to make some cardboard discs, and the cardboard discs I'm going to cut out, and I'm going to cut them out quite roughly to start with, and then I'm going to cut them down. And I want them to be the same size as the copper coin. I don't want them to be smaller, and I don't really want them to overhang an awful lot. So I'm going to cut out the cardboard disc, and actually you could use felt, you can use fabric, you can use blotting paper, but what we need is a medium that we can soak up the electrolyte. In this case the electrolyte is going to be salty water, a saturated solution of salt. I'll show you that in a sec. And we're going to cut out the discs. And what we're going to do is we're going to soak them in the salty water. And these will be a source of electrolyte for our battery. So I'm cutting these out. And I've got 4 quite rough circles, not great at all. And I've got a bowl of saturated salt solution. You can see that the salt crystals in the bottom, because there's as much salt as will dissolve in the water, and I'm literally going to drop the discs in there. That's 4, and I'm going to carry on making some more, but I'm likely to edit that out of the video. So 4 will be 5, will be 6, will be 7, 8, 9, 10. So that will be 10 cardboard discs. So I'm just going to cut this one out. So you should realise I'm not great at cutting. I guess if you were doing this commercially you could buy felt pads, circular felt pads, or I think the original Voltaic Pile in the liquid used leather, thick leather, I don't suggest you use that these days, partially because getting thick leather of the right thickness is probably quite difficult, but also because of, I suppose, ethical considerations in terms of using those kind of animal byproducts in the classroom as a demonstration. Also, cardboard is easier to cut, use it as a form of recycling. So let's cut out the discs. Cut out the discs. And you find that actually the electrolyte, so I'm using salty water, saturated solution, but actually you can use distilled vinegar. You need any electrolyte, you need something that is either an acid or an alkali, and some form of ionic solutions, so some kind of salt dissolved in that, so that it allows electrical current to move. You need to make it a conductive medium of some description, but by far the simplest and safest in the classroom is a salty water solution. You could put distilled vinegar in it as well, and there's no real issues with using that in class. You might get a higher voltage out of the battery when we set it up, but again we've also got the consideration of having all that vinegar floating around, and someone's bound to have a paper cut of some description, but actually there's no real issues. I'm just going to dunk these under the water now, dunking the discs in the water, in the salty water solution, and whilst they're soaking up the salty water, we're going to make a disc of aluminium, and we're going to do the same way. I've got a sheet of aluminium foil, tin foil, aluminium foil, which I have folded over numerous times. He said, singly demonstrating his inability to unfold a sheet of aluminium foil. So a sheet of aluminium foil that I folded a number of times. Fold it once, fold it twice, and fold it again. And onto that I'm going to draw around a 2p, same as before, and cut them out. But this was particularly fiddly, so I did it previously. Because what happens is the aluminium discs themselves begin to stick together. So not only have I kind of messed up them, cutting them out, it's quite a fiddly process. But in terms of doing it in class, no harm. Scissors, I suppose, something to consider. But cutting aluminium foil in a circle, not that difficult. We want as many aluminium discs, foil discs, as coins, as copper coins. And so we've got aluminium, we've got foil. And what I'm going to do is I've 3D printed something here, which is going to allow me to make up the stack. Because as we stack these on top of each other, not only do they become unstable, you get the liquid everywhere, and actually some way of keeping it stable allows you to push it down to make better electrical contacts. So what I'm going to do is I'm going to take the 2p coin, put it at the bottom of my stack, and then I'm going to alternate between the brine soaked cardboard and then the aluminium foil. But underneath it at the very bottom I'm going to put a strip of aluminium, just so that when I come to measure the voltage I can get some crocodile clips and I can clip it on at the bottom here to measure the voltage easy. So I'm going to start now by taking the first coin and putting the coin in my little contraption I've manufactured, and then on top of that now I'm going to take some, leave it by there, but I'm going to fish out a salty piece of cardboard, and I'm going to put that in my stack, and then on top of that I'm going to add a piece of tin foil. What I really want is just one layer. There's a piece of tin foil, and I'm going to pop that in, and that is one cell. That is what that layer of copper, electrolyte and aluminium is called, a cell. It's not a battery at this point, it's just a cell. But what I can do is I can bring the voltmeter in and set it to, well, let's be optimistic, 2 volts. And I am going to clip my crocodile clips onto the bottom. We'll see which way around it goes, and that's an investigation for the children. But I'm going to clip my positive crocodile clip on the bottom. left onto the bottom, and then I'm going to get my other lead from my multimeter, and I'm going to just tap it on the top on the aluminium foil, and we'll see what voltage is generated. So there we go, we've got 0.5 volts, half a volt, from one stack of coins. So if I come along now and I add another coin on top of this, another 2p coin onto the sandwich, and then on top of that I'm going to add another piece of brine soaked cardboard, and then on top of that I'm going to add another piece of tin foil. Conversation for the children becomes, let's predict what voltage we've got. So we've got two stacks. We had 0.5 volts before for one stack. I've got two stacks now. What's my voltage going to be? 0.62. So the voltage has gone up, not doubled, and that is source of a conversation. Would we expect it to double? And I'm going to go again. I'm going to add another coin, and I'm going to add another piece of cardboard, and I'm going to add another piece of tin foil. So now we've got three. So initially, let's write these down. Initially I had 0.5 something, then I had 0.6, was it 0.62? So now on the third time, measure the voltage across the top one, 0.58, going down. It's interesting. So conversation about why that might have gone down. Going to give it a little bit of a squeeze, make sure it makes good electrical contact. See what's going on here electrical wise. 0.5, a stack of 3 here now, 0.5, 0.6. Interesting how variable it is, isn't it? What if I really squeeze it down? Really squeeze it down. 0.56. Okay, let's write that down, 0.56. So what I'm going to do is I'm going to jump ahead now to putting many layers in. Let's see what happens. So again, I'll edit the video. So we've got 3 layers. We've now got 4 layers. Let's pull off the tin foil layer there. Is there one layer there? Yes, there is. So that's 4 layers. What does 4 layers give us? 0.56. Doesn't seem to be going up, does it? That's interesting. If I now add another coin and another piece of cardboard and another piece of tin foil, have we gone up again? 0.63. Doesn't seem to be doing anything, does it? The more I go up, if I really squeeze it down, we notice the liquid coming out, we notice the electrolyte coming out. Really squeeze it down and measure the voltage now. The voltage has dropped considerably. That's interesting. Why might that be? Why might the voltage have dropped? We've got something shorting out here. If I go down, it's interesting that the voltage is, yeah. Much faffing about later, we're back in the room, and what I've discovered is that cutting out the discs of aluminium, whilst it works, the aluminium has got to completely cover the coin in the layer below. Otherwise what happens is you start getting the battery shorting out. So we've gone back to the drawing board, and instead of using aluminium discs cut out of, well, the same, in theory, the same size as the 2p coin, it just doesn't work. It doesn't cover them effectively. So I'm going to can the aluminium disc idea, move those to one side, and what I've got instead of aluminium discs actually are some 10p coins. Okay, now 10p coins themselves won't work because the difference, the composition of the 10p compared to a 2p, they're actually an alloy, and actually you don't get much voltage produced at all. But what I'm going to do is I'm going to take the 10p coin and I'm going to wrap it in aluminium foil, because a 10p and a 2p are almost the same size. 10p is slightly smaller. So if I take a 10p coin and I completely wrap it in tin foil, okay, completely wrap it in tin foil so that there's none of the 10p visible. We've completely covered the metal. That's what we're going to use as our aluminium discs, okay, because it's easier to get hold of than aluminium itself, as sheets of aluminium cutting out discs. So I'm going to make some 10p coins like this that I've covered in aluminium foil. So there's 1, there's 2, there's 3, and there's 4. So I've got 4 of those coins covered in aluminium foil, and I'm going to go back to my little contraption I've made here, and I'm going to attach the voltmeter to the bottom coin, cut the bottom coin like this, and I'm going to take on top of the first. You can imagine that's just the bottom layer now, okay. So I'm going to make a sandwich now of a 2p coin, some fresh electrolyte, cardboard electrolyte, which has got to cover the coin as best we can. If there's any kind of hanging over bits, I'll pull them off, I'll trim them down. Okay, because what we now want when we put the 10p coin on is we want the 10p coin not to touch at all the coin underneath, because if it does, it will short out. So that's where this has all been going wrong for me. So I'm going to put another disc on it, another disc of the electrolyte, and I'm just going to move them around slightly so they completely cover. Okay, it shows you how inaccurate my cutting out was. That in itself could be part of the lesson. But there we go, it's good enough for me. And then I'm going to take my 10p coin I've covered in aluminium, and I'm going to pop it on top. And this time they won't touch because they're slightly smaller. Okay, so if I now take this sandwich and put it in my little contraption so they all stand up straight, and I measure the voltage across the top, it's 0.5 volts. Okay, 0.547. Let's write that down. And I'm now going to make another stack. So on top of the aluminium foil, I'm going to add another copper coin, and I'm going to make another sandwich of a copper coin, some electrolyte, now that one's a good fit, some electrolyte, and one of my coins wrapped in silver paper, and I'm going to add that on top. In fact, there's a little gap there, so what I'm going to do is I'm going to get another one of my discs of silver paper just to make certain that there is none of the underlying coin visible, and I'm now going to add that onto what's there already. Push it down so they make contact. Okay, so it was 0.547 before, so what is it this time? 0.97, let's say. So that's not quite twice, but it's not far off. So I'm going to do the same thing again. And on top of that aluminium, I'm going to add a 2p coin, and then on top of the 2p coin, I'm going to add some electrolyte like that, and then on top of that I'm going to add my silver coin, my aluminium covered 10p coin, and I'm going to put that in my little stack. And this time, what's the voltage going to be? This time the voltage is 0.9. Actually, it's interesting, it's not gone up, so have we got a short of some description going on there? Yes, we have. That's interesting, that. Depending on where I push it. So there's something interesting with that layer I've just created. Something must be hanging over. Oh no, yeah, look, there we go. Look, you see the electrolyte underneath is hanging over. So it shows how fiddly these batteries are to make. Trimming it all down. Okay. Let's put this back in there. Let's see what this looks like. Let's put it that way in. Separated by the electrolyte. Let's put that back in. What does it measure this time? 0.98. Okay, so literally it's a fiddle fest. Let's give it a squeeze. It's gone down even more. This is really not a doable practical, is it? Funny, isn't it? You start doing these things and you think, or it'll be interesting for teachers to do. A practical activity. I guess you can, what I was trying to get to was the idea that the more coins you put in the stack, the higher the voltage. And in some kind of weird kind of way, I've demonstrated it, but it's just so fiddly, isn't it? Coin, electrolyte, coin, electrolyte, and then the silver coated coin gives me about 0.5 volts, doesn't it? Do this again, it's about 0.5 volts. Look at the voltmeter, 0.5 volts. Okay. In theory, if I add another stack on top of that of a copper coin and then an electrolyte on top of that, and then another copper coin on top of that, let's make sure the electrolytes are completely covered the copper coin underneath, don't want them to short out. At this point, if I then take another one of these coins and I put it on top of there, we now should be about 1 volt that we see. And I doubt it probably is because it's less fiddly now. 0.85, 1.9 is yet 1.9. I've got something shorting out. What's really interesting is a demonstration for teachers. It was supposed to work. I was supposed to be able to show you, let's draw a graph, yeah? Let's turn this into a graph of the voltages against the stack of coins. So in theory, I was going to produce coins this way and voltage this way, and I was looking for some kind of positive relationship like this. The more coins, the higher the stack, the higher the voltage. That was in theory where this was going to go. But actually, it just doesn't. It's a faff, you know, it works. It kind of works. We produce a voltage. So I guess we could demonstrate the whole idea of a single cell, you know, a coin, an electrolyte, and another coin, like this. That sandwich is called a cell, and it's equivalent to a AA battery. So if I measure the voltage across that, it's 0.5 volts. In theory, if I add another stack on top of that of another coin, another electrolyte, we're drying out now a little bit, but another electrolyte and another coin, it should be roughly twice the voltage. It should be roughly twice the voltage. So that should be about 1 volt. And I guess it wasn't far off there, but it's very dodgy and very delicate. 0.8, 0.9. So I have 2 in the stack is double. And if I add a third one now, there's a bit of the coin underneath you can see. So I'm just going to cover that with silver so it hides it completely. And then if I take another copper coin, put that on there, another electrolyte on there, and another copper coin on there, in theory that should be 3 times what we started off with, so it should be about 1.4 volts, and it's not. 1 volt, clearly over 1 volt. It's clearly going up a little bit, but it's incredibly dodgy and it's not reliable enough to do in school in terms of the investigation I was looking for. So actually I'm going to abandon it there and come back with something else actually, because just picking up the coins themselves has led me to think about something else. So I shall be right back. So back at it, and what I've got in front of me now are 2 of the coins that I was going to use for making the battery, the cell, the Voltaic Pile experiment. It just didn't work. What I ended up doing though was having a bit of fun cleaning the coins. Again, something you can show your students is one of the best ways to clean copper coins. The kids really love cleaned copper coins. So what I'm going to do is there's a 2p coin here, and I'm going to half cover it with masking tape. And I've got another 2p coin here. It's a different vintage, and I'm going to half cover that one with masking tape like this. Okay. And then what I'm going to do is I am going to get a lovely cotton bud specifically bought for the purposes of cleaning things. And here it is, rather lovely. And I'm going to take the solution we had previously, which was the salt solution, and I'm just going to dab some of the salt solution on the coin, and not a lot happens, you'll see. But I've now got some vinegar. Now ideally I should use some distilled vinegar, but this was the only vinegar I could lay my hands on. So on top of the coin, on top of that salt solution, I'm going to put a drop of vinegar. And then I'm literally going to agitate it backwards and forwards. Nothing clever, I'm not scrubbing. This isn't an abrasive brush, it literally is a cotton bud for the purposes of cleaning. And even without agitation that one was going, wasn't it, quite well? Well, it's soaking under the cloth, so it's not going to be as good as I thought it was. Maybe a bit more salt solution. So the interaction between the salt and the vinegar produces a series of chemicals. It's quite complicated and probably beyond what we'd want to be explaining to the children. But the salt, sodium chloride, and the vinegar, ethanoic acid, create a series of compounds that dissolve the copper oxide off the face of the coin, and it's probably the most effective cleaning solution you can get before you start getting into really quite abrasive, dangerous chemicals that you probably wouldn't want the children to be handling. You can see where's one of the questions is, where's the dirt gone? Well, it's on the cotton bud. But actually, as an example of chemical reactions, and I don't know if you're doing potions or what else you might be doing for chemical reactions, but it's really quite a nice chemical reaction because it's quite safe. We can handle whatever's going on here, we can handle in class. Worst case, it's salty water and vinegar. And yes, if you've got paper cuts, and yes, if the children have got paper cuts, it'll be perfect at identifying them. And it'll end up in eyes and all that kind of stuff. But they're household chemicals, aren't they? Salt and vinegar. So you could give them goggles and you could give them gloves. But as long as hands are washed, and there is that kind of health and safety warning about not getting this in your eyes and putting it in your eyes, actually it is literally just salt and vinegar. Hands do need to be washed, though, before food is consumed. But that's just good practice anyway, isn't it? So I'm going to give up on this now. You see the dirt on here. I'm going to remove the masking tape, and then we got two sides of the coin. Actually, it's all kind of bled underneath, and that's how the coin was before, and that's how the coin is now. Now, when I did it, I didn't do it like that. I think that's gone quite well as well. You can see the difference. When I did it, I put the coin in my hand. Well, in fairness, I got the coin wet, salty water, and then I got some vinegar, and I tipped the vinegar onto it, and I rubbed it round on my hand. We wouldn't advise necessarily you get the children to do that, because chemicals aren't toxic, but they're now on my hand, and it's inevitably going to get flicked to places. It's going to end up in my eye, it's going to end up in someone else's eye. Fortunately, it is just salt and ethanoic acid, salt and vinegar. Okay, there is some tarnish there on this coin that's not coming off. And literally, by working it through your fingers, skin's quite good, skin's quite abrasive. With the salt and the vinegar, we end up being able to take the majority of the tarnish off. So what was supposed to be a video about making batteries has ended up on a video about cleaning coins. But children love having the clean coins. Often they've never seen them before, and often this is used as an investigation into household chemicals, you know, soap, water, lemon juice, tomato sauce, brown sauce, other things that actually do clean coins. How scientific that is, I don't know, but it's always a bit of fun. And children are often surprised at the colour of a copper coin, and the colour it would have been when it was freshly made, freshly minted. Nice bit of vocabulary there. We can talk about things being minted. Okay, and I would rinse that off now in water. So that's about it for coins. batteries were a bust, but we've ended up having a good clean of some coins and actually spinning that out into an activity that could be used in class. So thanks for watching. If you like this video or you like seeing me mess things up, please like and subscribe, and I'll be back again shortly. Cheerio!